Hi, thanks for joining me here today. So I'm going to be speaking about the intersection of HPC, AI, and quantum computing, among other technologies here. I'll be speaking on behalf of my colleague Santosh, who was not able to make it today. But what I want to really focus on, just from the outset, is what it means to have these different technologies together. What does it mean to harness all of these technologies? It's more than simply providing them to end users, making them accessible, and giving some credits. Really, to harness these technologies, it means making them so easy to use, so easy to put together and to reconfigure that end users can start to build more interesting applications and use these technologies all together in single applications to the best of their ability. At the same time, from the administration perspective, for instance, for HPC data sysadmins, for cloud sysadmins, it becomes very important that as new devices come online, as user requirements change, the system is sufficiently reconfigurable that it does not require an exorbitant amount of time and effort. So with this new landscape, what do we have? Well, traditionally in HPC, you have a large compute cluster, users log into it, they access CPUs, sometimes they access GPUs, but in the past 10, 15 years, this has really changed. It's now commonplace to have GPUs in supercomputers. And I think in the next 10 years, it will become commonplace that we will see QPUs in supercomputers as well as other devices that come onto the market. Now, you see a little spectrum here on the bottom: CPU, GPU, FPGA, QPU, ASICs, other AI chips that will come out into the market. It's a lot to manage, but at the same time, it presents an incredible opportunity for end users. We have more devices to play with than we've ever had before. Now, let's take a look at, what does a typical research lifecycle look like from initialization of the concept all the way to production. We can break this into two categories. So on the research side, we have this cycle of ideation, experimentation, writing a paper or producing a POC. And really what's important here is going through this cycle as fast as possible. Oftentimes we have very fluid environments that we're working with. Things change quickly. The types of experiments that we're doing are going to change. The types of devices that we're going to use are going to change. But eventually we fix certain constraints and we say, okay, this is ready for production. When we take it to production, what we want to optimize for is not the speed, but rather the reliability and the security. And so in the production lifecycle, we have development, deployment, monitoring, optimization, and so on and so forth. Now, it becomes very important to not only make this something that's easy for researchers to do, but make it easy for researchers to bring things to production as well. We see this in AI, in quantum, where the domain experts and the quantum algorithms researchers need to be able to take an idea to production in order to demonstrate the value, not just in terms of whether or not their solution works, but whether or not it's cost effective with today's technology. And that cost effectiveness is really a crucial part of HPC today. Now, if we take a look at this emerging heterogeneous computing ecosystem, what does it look like? So we can break it roughly into three different layers. We have an application layer, we have an orchestration layer, and we have a hardware layer. Now, I tend to focus on the middle layer, the orchestration layer, in my line of work. What that means is bridging the two other layers so that people who write applications can easily interact with the hardware layer. And at the same time, it means that people who manage the hardware layer can easily reconfigure their hardware and reconfigure what they present to users without disrupting end user applications. So typical applications that we would see today that use some of this advanced computing hardware: quantum machine learning, quantum chemistry, optimization in finance, drug discovery. There are a lot of really promising areas where people are using this technology. At the hardware layer, of course, we have all of the traditional things that I just mentioned, but even within each of these boxes, you could break it out into further categories. So for GPUs, we have different architectures, we have different models that come online, it seems every year now. For QPUs, there are many, many different types. Each has different strengths, each performs in a different way, each is evolving in a different way. And then we have other custom chips that maybe we haven't even seen yet that are going to come on the market. And in the middle, what we see is a somewhat fragmented orchestration layer. In the past, it was not very common for an expert in GPUs to also be using FPGAs or ASICs or QPUs. And today, even, it might not be common for people who use quantum devices to be experts in, say, CUDA programming at very low levels. But with a good orchestration layer, we can unify all of this and make it so that not only can end users reroute their tasks flexibly to different devices and benchmark them and test them and evaluate them, but people who manage the hardware layer can also exchange devices without disrupting user applications. So just a simple example here. Consider this quantum classical hybrid workflow. So we have perhaps an AI model that's running on a GPU. It's going to make some structure prediction for a drug discovery. This is then going to run a simulation using a QPU, calculate some properties. It's going to use a CPU for some optimization. You'll have some back and forth between the quantum and classical devices. The AI model is going to feed into this as well in order to guide the experiment. And even from this very simple example, we can see that it involves a very complex pattern of data movement. Now, if all of these devices are in one data center, maybe it's not so bad. But what we increasingly see is that users are not just using a single data center. They're not even using a single region in the cloud or a single cloud vendor. Oftentimes, users have very complex requirements, whether it's due to data residency, whether it's due to certain business partnerships that they want to achieve. And this means that oftentimes, even in this simple workflow, these devices may be located in very different locations. They may be provided by different vendors. And so this provides a lot of different challenges. I'm going to speak now about some of the challenges for end users or developers. Now, for these devices, there's a little bit of a polyglot problem. And what this means is that for each of these devices, we're using different languages, different APIs, different ways of accessing them. Even in the quantum space, there's not yet a standardization of how users are going to interact with these devices. And so we see a few different challenges. So anyone who wants to become an expert needs to master multiple programming paradigms, not just languages. They need to be able to optimize algorithms for different architectures. They need to ensure code is portable as well as maintainable. What that means is that we're not building these high-performance applications to run on a single device that will never change. It is incredibly important that something that runs today can also run tomorrow and 6 months from now. But it's not all bad. We have some solutions. We can build abstraction layers and unified APIs. We can use tools like AI to auto-tune and guide adaptive algorithms and workflows. And we can have collaborative development and knowledge sharing between different communities. And as we bring all of these technologies together, we also bring the communities together. And this is very important for the health of the ecosystem. We also have a slightly different complexity for heterogeneous development. So whereas traditionally in an academic space, maybe you're going through a simple process of develop, test, analyze. In an industry case, maybe you're doing something slightly more complex with a few different technologies. Maybe some of them are on premises, some are on the cloud. But once it becomes a heterogeneous workflow, it becomes very difficult to maintain, deploy, manage all of these different components in a way that they're going to continue to work together as they're built out. And then finally, I really want to highlight the difficulty in productionalizing non-CPU workloads. There are really high stakes here. So if you get it wrong, it could be the difference between profit and no profit. What that means is that even though these devices are available, even if they are proven to do things that classical computers cannot, if their cost is so high, both in terms of dollars as well as climate impact due to energy costs, this is going to be a problem for the space. It's going to slow down the space. And so I think it's very important that as we build out these tools, we also make sure that they are sustainable, that they are able to demonstrate the value that we claim that they do. Now on the administration side, we also have some problems. Traditionally, an HPC sysadmin has a data center that they need to manage. It consists of a bunch of rack servers. Maybe there are some GPUs in there, but this is changing. Even with the introduction of the latest NVIDIA GPUs, we're seeing that data centers need to be completely redesigned for larger power consumption, for higher power density. And when we bring quantum devices in as well, there are going to be additional constraints. So traditionally, we're going to have fairly simple requirements, whereas now we have more complex requirements. We have job scheduling across different architectures, which is going to be completely different. The performance monitoring and optimization across these devices is going to be very critical for understanding the stability of them over time. We have cross-platform security and compliance, which is maybe not a problem at the POC level, but is definitely something to think about at the production level. And then we have dynamic resource provisioning and scaling, which is going to be important as we want to use these devices efficiently. And then finally, I want to just say, when we think about orchestrating all of these heterogeneous jobs, it's very different when we try to merge these technologies. So traditionally, in a batch scheduler, you're going to request some resources, you're going to use them, they'll be retired and sent to the next user. When GPUs enter, you have to do a little bit of sanitization on the GPU memory, and that takes some time, so there's a little bit different life cycle. For quantum devices they enter in, you need to introduce calibration, other types of events. And so each of these devices is coming in with different constraints in how they can be passed along to different users. And if we want occupancy to remain high and users to remain satisfied, then it's important that we maintain a high throughput. So one of the other challenges that I just want to highlight real quick is taking this from research to production in the sense of these pieces in the middle here, so monitoring, automation, and compliance. If this is something that we can provide out of the box through good orchestration tools, then it means that with very few changes, we can take something that was a research problem or a POC and put it in production, start giving it to users or customers, making money from it, and ultimately demonstrating real-world business value. So this is, again, something that is quite different in this landscape now. Now, current solutions tend to focus on one of a few areas. You have development tools, you have your production environment tools, your heterogeneous compute tools, but there's not really a unified solution yet. Some of the things that we're looking for are, for instance, seamless workflow design across different architectures. We need intelligent resource allocation and optimization, and we need unified monitoring and management of these devices. So it's really important for us to understand in a very heterogeneous data center, or even something that's distributed, how to look at this as a whole and work with it and manage it and understand it as a whole and not just a collection of different devices. So what we work on is a tool called Covalent. Covalent attempts to address some of these problems. So as opposed to some of the legacy tools, Covalent is designed thinking about these problems from the outset. So that means we're thinking about how does AI play a role in HPC? How does quantum play a role in HPC? How do some of these other devices play a role? And so what we're doing here is we're providing a variety of features. Many of these are table stakes for HPC, but some of them are going to be new. This, for instance, includes service mesh when we want to have AI agents at scale. It includes pricing and billing constraints when we want to have dynamic jobs that can run perhaps up to a certain budget amount. And we have more complex queue management as well. And this allows us to interact with these heterogeneous compute resources in a more unified way. So that from the user perspective, users are really thinking about how many CPUs does my job need, how many QPUs, how many GPUs, maybe which country does it run in. But they're not thinking about how do I get my code onto this particular compute cluster, or how do I get my code to work with this particular cloud vendor. So the difference is very clear, I think. On the left-hand side, you can see quite a tangled mess of tasks. Oftentimes, in real-world use cases, we see workflows which are very, very large, but at the same time, they're difficult to manage. And nobody really cares about these tiny little individual steps until something goes wrong. And so what this means is that with a tool like Covalent, we can track and trace and monitor all of the different inputs and outputs through the checkpointing, trace errors, trace logs through distributed systems. And this means that through this interface, through this platform, we can understand these resources as a whole and use them as a whole. And it empowers users to build applications that they couldn't build before. If you wanted to build your own ChatGPT, or 10 of them, or 100 of them, each of them specializing in different things, and interact with them in a scientific workflow, or use them to launch their own scientific workflows in order to get better results. This is the type of thing that we aim to tackle. So I think this gives you a sense of where we're headed with Covalent. In the past, we're really looking at siloed compute resources. But not too long from now, we're really going to have integrated heterogeneous compute. And this means that we're going to start seeing this collection of resources being unified at the data center layer. But even further beyond that, we're going to start to see this change a little bit more. This is really the vision for fully democratized advanced computing. It means, like I said at the beginning, we're not just harnessing these resources by giving them to users, we're making them so incredibly easy to use, so incredibly easy to reconfigure, that users can build the most incredible applications that we haven't even dreamed of yet. So I encourage you, if this message resonates with you, we have documentations, tutorials, examples, an open source community, and we have a booth next door. So please do stop by, and I'd be happy to talk more. Thank you very much.